For the case of geometrical similar indentations, maintaining the solid angle phi constant, this is the diameter of indentation for the diameter of indenter d1. Okay, so this is the radius, so it can be about d1 by 2. And for the case of diameter of indentation d2, when using a different size indenter, that is d2 by 2. So by maintaining diameter of indentation to the diameter of indenter is equal to constant, that is by producing geometrically similar indentations, the hardness values does not vary with load. So the Brinell hardness number, it does not depend upon the load, it does not vary with the load if the ratio P by D square is maintained constant. By maintaining this ratio, load divided by the diameter of indenter, by maintaining this ratio constant, one can produce geometrically similar indentations. Then only the Brinell hardness number, it is independent of load, or else the Brinell hardness values will vary with load. So by maintaining P by D square is equal to constant, Brinell hardness values does not depend upon load. So this is a figure which shows the geometrically similar indentations, that is small d by capital D. This is the dia of indentation and this is the dia of indenter. By maintaining this ratio constant, the hardness values do not vary with load. So the loads, the standard loads that are used in the case of Brinell hardness are 3000 kg for the case of hard materials. 3000 kg is used, and 500 kg for the case of soft materials. So these are the standard loads that are used for the case of Brinell hardness. 3000 kg for the case of hard materials, examples of ferrous materials for ferrous alloys, and 500 kg for non-ferrous materials. And the diameter of the indenter is about 10 mm, which is hardened steel ball. So the range over which Brinell hardness is used is 16 HB. HB stands for Brinell hardness, that is for the case of soft aluminium, to about 627 Brinell hardness, which is for the case of hardened steels. So this is the range over which Brinell hardness is used. 16 for the case of soft aluminium to that of 627 for the case of hardened steel. So the formula and the derivation that was explained earlier, where Brinell hardness number is load divided by surface area of indentation. Surface area of indentation, which is given by the formula P divided by pi d by 2 into capital D minus square root of capital D minus small d square. So the load is known, diameter of indenter capital D is known. By measuring the diameter of indentation by using a low power microscope, which has an inbuilt scale. So using that, diameter of indentation is measured. and that is substituted in this formula. Load is known, diameter of indenter is known, that is 10 mm, and small d, which is the diameter of indentation, that can be measured by using a low power microscope which has an inbuilt scale. So substituting the values, one can obtain the Brinell hardness number. So Brinell hardness method, which uses steel ball as indenter, so that has a problem when it is used for hardness numbers greater than 444. For hardness numbers greater than 444, the problem that is with the case of steel ball indenter is the diameter of the indenter, it undergoes flattening, it undergoes distortion at such very high values of hardness. When testing for very hard materials, the same indenter cannot be used for hardness greater than this number 444 because of the flattening and distortion of the steel ball. For hardness values greater than this, a tungsten carbide ball is used. So tungsten carbide ball is used for hardness values greater than 444 to that of 627 Brinell hardness. So this is the problem we have for the case of steel ball. When testing for very harder materials, there is a possibility of flattening and distortion. Because of this flattening and distortion, it gives rise to incorrect hardness values. Thereby, for the greater hardness numbers greater than 444, the indenter, it is replaced by means of tungsten carbide. So when using tungsten carbide ball as an indenter, then it is represented as HBW, where HB stands for the Brinell hardness and W stands for the tungsten carbide ball as an indenter. When steel balls are used, the hardness number is represented as HBS. S stands for steel ball and W stands for tungsten carbide. So now the advantages and disadvantages of Brinell hardness test. The advantages of Brinell hardness test is that the size of the indentation is very wide when compared to the other indentations, when compared to the other indentations produced by different hardness tests. So this Brinell hardness test produces a deepest and widest indentation. This is an advantage as well as an disadvantage. Advantage is that it is less sensitive to the surface irregularities. Even though the surface is rough or there are some scratches on the surface, so Brinell hardness is not sensitive because of the widest and deepest indentations produced by this method. As well as the disadvantage is that because of this widest and deepest indentations produced by this method, there is a chance for the potential site for failure to take place on the very stressed parts or for the regions which are in the very highly stressed regions. So there may be a chance of failure. That means a crack initiation may take place, crack propagation occurs in service. And moreover, for the finished products, one cannot use the Brinell hardness because of the very widest and deepest indentation which is produced by this Brinell hardness. And moreover, for very small precision parts and for testing the layers or for testing the surface coatings, this Brinell hardness test cannot be used because of the larger depth and the widest of the indentations produced by this method. And another disadvantage of this Brinell hardness is unless until this load by square of the diameter of indenter is maintained constant, the Brinell hardness will vary with load for the same material. So P by D square is equal to 30 for the case of steels and P by D square is equal to 5 for the case of soft materials, that is for the case of non-ferrous materials. So maintaining this ratio, one can obtain the Brinell hardness values that do not depend upon or vary with load. So this ratio has to be maintained in the case of Brinell hardness, or else it will vary with load for the same material. Mayer hardness is more meaningful when compared to that of the Brinell hardness. The reason is it has taken into account the mean pressure between the indenter and that material. But Brinell hardness is most widely accepted hardness method than compared to that of Mayer hardness. And moreover, Mayer hardness is not valid at low loads, because at very low loads the Mayer's law is not obeyed, because at very low loads the material do not develop a complete plastic region below the indenter. Thereby there is a limit below which Mayer's law is not valid. Even though there are certain limitations, Brinell's law is most widely accepted for industrial purpose. As there are certain limitations for the case of Brinell hardness, so this prompted the development of other indentation methods. The other indentation methods are Vickers hardness test, which uses a diamond pyramid indenter, a square based diamond pyramid indenter, and another hardness indentation hardness method is Rockwell hardness. Vickers hardness is developed by Smith and Sandland, R. Smith and G. Sandland. In the year 1926, R. Smith and G. Sandland has introduced a pyramid shaped indenter, and Rockwell indenter, it was introduced by Stanley Rockwell in the year 1919. So Vickers hardness method, which is also known as DPH, diamond pyramid hardness, because of the shape of the indenter. The shape of the indenter is square based pyramid and the material is diamond. So this Vickers hardness test, it is independent of load. That means the hardness values do not vary with load for the same material when the loads are greater than 5 kg force. So the range over which the range of loads for the case of Vickers hardness test is from 1 kg to 120 kg force. So this is the range of loads that are used for the case of Vickers hardness test, which uses a square base diamond pyramid as indenter. The included angle between the diagonals is 136 degrees. The included angles between the diagonals is about 136 degrees. This is a specimen and the indenter. The included angle between the diagonals is about 136. The reason for using this angle is Brinell hardness, it varies with load. In order to minimize this variation, that the Brinell hardness, it changes with the load, the diameter of indentations should be about 25% to 50% of the diameter of indenter. So the loads that are applied, it should be such that D, that is the diameter of indentation, it is about 25% to 50% that of the diameter of indenter. Within this range, Brinell hardness values, they are independent of the load. So small d is, it should be in this range 0.25 to 0.5 times that of d. Average of 0.25 and 0.5 comes to about 0.375 diameter. So this is the ideal dia of indentation. So based on this ideal diameter of indentation, when tangents are drawn, the angle between the tangents is 136 degrees. So Smith and Sandland, they have chosen this angle because such that there will be some similarity between the Vickers hardness and that of the Brinell hardness values, because Brinell hardness, it is very well established by that time when they have introduced this pyramid indenter. So the included angle between the tangents drawn to the diameter of indentation, which is about 0.375, it is about 0.375 times the diameter of indenter. So this is small d, that is the dia of indentation, which is about 0.375 times the diameter of the indenter. So when tangents are drawn, the angle is found out to be 136 degrees. So this is the basis for the Smith and Sandland to choose this angle in the case of the square base diamond pyramid indenter, such that there will be some similarity between the Vickers hardness and that of the Brinell hardness test. So Vickers hardness test, it is given by VHN, Vickers hardness number, is equal to load divided by the surface area of indentation. The one advantage of using this pyramid shape indenter is that even with increase in load, the shape of the indentation do not change, whereas for the case of spherical ball indenter, the shape cannot be maintained constant, or that means the shape will change with increase in the load. So this is one of the advantage of using pyramid shape indenter, is that the shape do not change, only the size will vary, but the shape will maintain as same. So geometrically similar indentations can be produced by using this Vickers indenter, that is the diamond pyramid indenter. And another advantage of this is, the first advantage is geometrically similar indentations can be obtained by this method because of the shape of the indenter. Second is, the hardness values do not vary with load, that is above 5 kg. If the loads are used above 5 kg, and for the case of an homogeneous material, the hardness values are independent of load, they do not vary with load. So this is the second advantage, it is hardness values are independent of load for greater than 5 kg load, and geometrically similar indentations are produced by this method. Third advantage is, Vickers hardness test can be used to find out the hardness of various metals and alloys, ranging from the softest material to the hardest material, as well as it is also used to find the hardness of coatings given on the surface of that materials, to find out the thickness of the hardened layers, carburized layers, to find out the coatings on thin sheets also. There is no need to change the indenter for or the load for the case of Vickers hardness. Whereas in the case of other hardness methods, like for the case of Brinell, one has to change the indenter when testing for harder materials, that is for hardness numbers greater than 444, there is a need to change the indenter, to change into the tungsten carbide ball indenter because of the distortion and flattening of the steel ball. Whereas in the case of Vickers hardness, the diamond indenter does not undergo any distortion when testing for harder materials. So the same indenter can be used for testing harder materials as well as for softer materials. Even this method can be used to test the thickness of very small very thin materials, very thin specimens, as well as the coatings given, or the hardened coatings given like the carburized layers, as well as the coatings given to the materials. So one can determine the hardness of all these things by using this Vickers hardness without the need to change the indenter. So it provides a long range scale over which almost all the hardness of all the metals and alloys can be determined by using Vickers hardness test. So this is one more advantage when compared to Brinell hardness test. Then there are also certain disadvantages in the case of Vickers hardness. The disadvantages are that this method, it is not suitable for routine testing. This is most widely used for research purposes. Even though very accurate readings can be obtained, accurate hardness values can be obtained, but this is not suited for the routine testing, because one requires a very careful surface preparation, because the size of the indentation, it is less than 1 millimeter in the case of Vickers. When compared to Brinell, the size of indentation, it is of mm, whereas in the case of Vickers, the size of indentation, it is less than an mm. So very careful surface preparation is required for Vickers hardness test, as well as if there are any surface irregularities, one cannot go for this Vickers hardness test. One needs to carefully prepare the specimen, as well as measuring the diagonal length is also very important. If there is any error in measuring the length of the diagonal, it will lead to incorrect hardness values. So the indentation, it is the shape of the indentation, it is the square base diamond pyramid. So this is the shape of the indentation that is produced in the case of Vickers. Vickers hardness is given as load divided by the surface area of indentation, that is equal to VHN is equal to load by 1.854 into P by D square, where D is the length of the diagonal. This is equal to, small d is equal to the average length of diagonal. So in the case of Vickers hardness, one has to measure the two diagonals, this diagonal and this diagonal. Take the average of these two diagonals, square of the diagonal which is there in the denominator. So Vickers hardness number is equal to a constant, that is 1.854 into load by the square average length of the diagonal square, gives the Vickers hardness number. The units for Vickers hardness number is similar to that of Brinell's, that is kg by mm square. So if the indentation, once the indentation is obtained, then one has to measure. There is a microscope in the hardness tester itself. So once the indentation has been made, then the objective has to bring into position, and then one has to measure the lengths of these two diagonals. This is diagonal 1 and this is diagonal 2. Then average of these two diagonals is taken, and then it is substituted in the formula to get the Vickers hardness number. So this test is somewhat slower when compared to the other hardness test. So this is also one of the disadvantage of Vickers, and it cannot be used for routine purpose. So a comparison between a Brinell and Vickers hardness test. So Brinell and Vickers hardness, the hardness values are almost similar up to a value of 300. Beyond 350, Vickers hardness and the Brinell hardness are not similar. Brinell hardness deviates from Vickers, and the hardness values keeps on decreasing for the case of Brinells when compared to Vickers. The reason why there is a decrease in hardness values for the case of Brinell at hardness values greater than 350 is that the use of a hardened steel ball indenter for such high hardness values, that is for testing on very hard materials, the steel ball gets distorted, it gets flattened, which results in incorrect hardness values. Whereas the diamond indenter, it is not flattened or distorted when testing on very hard materials, because diamond is the hardest material, so it does not undergo any flattening or distortion when testing on very hardened steel materials. So this is the similarity between the Vickers and Hardness, which can be obtained up to the hardness values of 300, beyond which the Vickers hardness keeps on increasing, whereas there is a deviation of the Brinell hardness from Vickers hardness, and the hardness values are lowered beyond 350 hardness. So this is the comparison between the Vickers and Brinell hardness test. As it can be seen from the figure that up to 300, both the hardness values are similar, beyond which the Brinell hardness values, this is for the case of 10 mm dia steel ball indenter. The Brinell hardness, it deviates from Vickers, and the hardness values obtained from Brinell, they are very lower when compared to that of Vickers. The reason is due to the flattening and distortion of the steel ball indenter. So in the case of Vickers hardness test, a perfect indentation is that this is the perfect indentation obtained in the case of Vickers hardness test, perfect indentation. Whereas sometimes a pincushion type of indentation or a barrel shaped indentation can be produced, which results in increase in surface area or decrease in surface area. That is, for the case of a pincushion type indentation, it is similar. So this is an example of a pincushion type of indentation obtained in the case of Vickers hardness test, and a barrel shaped indentation. So pincushion shaped indentation, where the sinking of the material occurs and leads to a decrease in surface area when compared to that of perfect indentation. Whereas in the case of barrel shaped indentation, there is a piling up of the material and it leads to an increased surface area when compared to perfect indentations. When indentations are of barrel shaped or that of pincushion shaped indentations, then there is a slight change in the hardness values, that is due to a changes in surface area. This is with respect to perfect indentation. With respect to the barrel shaped indentation, the surface area measured is greater than that of perfect indentation, and for the case of pincushion indentation, the surface area, it is lower than that of perfect indentation. This is due to the sinking of the material, and this is due to the ridging up of or pile up of material, which finally results in increase in surface area of indentations. So when one obtains a perfect indentation, then one measures the diagonals of the two diagonals, diagonal 1 and diagonal 2, and the average of these two diagonals is taken and substituted in the formula. So one should be very careful in measuring the lengths of the diagonals, because if there is any error in measuring the lengths of the diagonals, it will result in incorrect hardness readings. Another type of indentation hardness is introduced by Stanley P. Rockwell in the year 1919. So this also uses an indenter which is either cone shaped diamond indenter or a ball shaped steel ball indenter. So this is also comes under the case for the indentation hardness test. The first type we have seen is Brenell, which uses a 10 mm steel ball. The second type is the Vickers hardness test, which uses a square base diamond pyramid as indenter, and this is one more type of indentation hardness test which uses either a diamond in the form of a conical shape, cone shape, or it is in the form of a steel ball indenter. So two types of indenters are used for the case of Rockwell test. One is a diamond in the form of a conical shape with an included angle is 120 degrees and the tip is about 200 micrometers. The second type of indenter that is used is hardened steel ball indenter. The diameter of the hardened steel ball is 1 by 16th inch, 1 by 8th inch, or 1 by 4th inch, or 1 by 2 inch. There are various diameters of the hardened steel ball depending upon the material to be tested or depending upon the application. That is either 1 by 16th inch dia steel ball, 1 by 8th inch dia steel, 1/4 inch dia steel, or half inch dia steel. So one is a diamond indenter which is in the form of spheroconical shape with an included angle of about 120 degrees and the tip radius is about 200 micrometers. So this indenter is also known as Braille indenter. This diamond conical indenter with a tip radius of about 200 micrometers, it is also known as Braille indenter. So Rockwell hardness test is of two types. One is Rockwell hardness, that is it comes under the macro indentation hardness test, and second type of hardness test is superficial Rockwell. So the basic difference between Rockwell and superficial Rockwell is Rockwell is used for bulk samples, whereas superficial Rockwell it is for thin specimens. This is for the case of thin specimens. For sheets we go for superficial Rockwell, and Rockwell hardness is for bulk samples. So the principle behind this Rockwell hardness test is Rockwell hardness test uses two types of loads. One is the minor load and second is the major load. Unlike the other hardness tests that we have discussed is either Mayer's or Brenell or the case of Vickers, where one measures the dimensions of the indentation. In the case of Rockwell, one measures the depth of the indentation. The hardness number is obtained by measuring the depth of indentation. The difference in depth of penetration of the indenter from the two load applications. The first load is the minor load that is applied. Initially a minor load is applied, and second a major load is applied. So the differential depth between these two load applications gives the Rockwell hardness number. So this is a basic difference between Rockwell and other indentation hardness tests. This measures the depth of indentation, whereas the other two which we have discussed measures the dimensions of indentation. Now coming to the minor load. The minor load that is applied for the case of Rockwell hardness is 10 kg, and for the case of superficial Rockwell the minor load that is applied is 3 kg force. So initially minor load is applied on the specimen, then a zero position datum is maintained. Next further major load is applied on the indenter. Then what is the difference in depth between these two load applications is measured, and that corresponds to the hardness number. The major loads that are used for the case of Rockwell hardness is about 60 kg force, 100 kg force and 150 kg force. These are the major loads that are used for Rockwell hardness. And for the case of superficial hardness, the loads that are used are 15, 30 and 45 kg force. 15 kg force, 30 kg force and 45 kg force. So these are the major loads, and 3 kg is the minor load that is used for superficial Rockwell. And for the case of Rockwell hardness, minor load is 10 kg and the major loads are 60 kg, 100 kg and 150 kg force are used. Rest all is similar between the superficial Rockwell and Rockwell hardness. Only there is a variation in the loads and the indenter sizes that are used. There are various scales which results due to the combination of the major load and that of the indenter that is used. In the case of Brinell, the units of hardness is kg per mm square, and in the case of Vickers, the units for hardness is also kg per mm square. But Rockwell hardness has no units. This is one of the important point, is it has no units. In order to specify the hardness measured using this Rockwell hardness, a scale has to be measured. The scale, it denotes a combination of major load and the type of indenter that is used, because as seen we use a different indenters, diamond conical indenter which is also known as Braille indenter, and in the case of ball indenters there are different diameters, 1 by 16th inch dia, 1 by 18th inch dia and so on. And there are various major loads also. We have 60 kg, 100 kg, 150 kg for the case of Rockwell, and for the case of superficial these are the various major loads that are used. So if one specifies the scale, it means a combination of the major load and indenter is fixed. For example, A scale, Rockwell A scale stands for 60 kg major load. Minor load is anyway 10 kg for the case of Rockwell hardness. For the case of superficial hardness, 3 kg is the minor load. But the major load varies and the indenter varies. So A scale specifies a load of 60 kg and the indenter that is used is conical indenter, that is Braille indenter, diamond conical indenter. And B scale stands for 100 kg force and the indenter that is used is ball indenter, 1 by 16th inch dia ball, hardened steel ball. Then C scale stands for 150 kg force, and again the indenter that is used is the Braille indenter, that is the diamond cone indenter. So while reporting the hardness values, one has to mention the scale. If one do not mention the scale, then Rockwell hardness number has no meaning. So HR 30 HRB indicates a Rockwell hardness of 30 is obtained by using a B scale, where B scale indicates a load of 100 kg and the indenter that is used is 1 by 16th inch dia hardened steel ball is used. So this is how one has to report the hardness for the case of Rockwell. Scale has to be mentioned, or else another way of representing the hardness is capital R and a subscript C indicates Rockwell hardness for C scale. RC 65, it indicates a Rockwell hardness of 65 is obtained when measured using the C scale. C scale is a combination of 150 kg force load, and indenter that is used is the braille indenter, that is the diamond conical indenter that is used. So this is how one has to report the hardness for the case of Rockwell hardness, and it has no units. So one has to be very careful in reporting the hardness for Rockwell. Scale has to be mentioned. And for the case of superficial, the various scales that are used are N, T, W, X, Y. These are the various scales which indicates a particular combination of load, major load, and the indenter that is used, where N stands for a 30 kg load and the indenter is diamond indenter. T scale is used for soft materials. W, X, Y, they are used for very soft materials, so which uses again a steel ball indenter, and T scale also uses a steel ball indenter, whereas N uses a diamond indenter. So like this, there are almost 30 scales for the case of Rockwell, both including Rockwell as well as superficial Rockwell. 30 scales are used. So these 30 scales, they are a combination of both major load and the indenter that is used. But most widely used scales in the case of Rockwell hardness are B and C scales, where B is major load is 100 kg force, and ball 1/16 inch hardened steel ball is used as indenter, and C scale uses a 150 kg force and diamond conical shape indenter is used. Diamond indenter is used. B is used for testing soft materials, non-ferrous materials, whereas C scale, it is used to test the hardest materials. And A scale also, it is used to test carbides. C scale, it is for very hard materials, and B scale, it is used for soft materials. A and C scale, they use same indenter, that is the diamond indenter, but the loads vary. So if the same C scale it is used for testing the carbides, there is a possibility of fracture on the specimen, or the diamond life will reduce. So for testing carbides, A scale is preferred, and B scale, it is for soft materials, and C scale, it is for hard materials. There are various scales, almost 30 scales, which are a combination of major load and that of the indenter that is used. So all these various 30 scales are provided in the reading material.